Greetings. Here are some quick notes on light propagation to accompany Chapter 1 of To Build a Star. So let's just discuss some basics of light that you likely well know, but we want to make sure that we're all working from the same starting point. So light, there's typically a wave picture and a particle picture or a discretized picture. In the sort of discretized picture, our light is composed of discrete quanta known as photons. Each photon carries an energy that is given by the frequency. So we just take Planck's constant and we multiply that by the frequency of light, and that gives us the energy. And the value for Planck's constant is in the textbook, or you can also Google it. Recall that the frequency is related to the wavelength via the speed of light. And our light source, right, when we want to describe this light source, it's not just individual photons beaming perfectly in one direction. Your light source in real life is going to have some angular extent, like how open of a cone do you have in your light source? That's described by the solid angle. And there's going to be some energy distribution, and that is what we call the spectrum. So basically, what is the wavelength distribution of your light source? When we describe a light source, there are different ways to think about that light source. Similarly, when we describe the light we detect, there are different quantities that we care about. So the luminosity, this is the energy released per unit time from a light source. The MKS unit is the watt, which is a joule per second. We often care about the flux. So that's typically when we're detecting light with, for instance, a telescope. So the flux, that's the energy per unit area and unit time, some distance away from our light source. So the unit there, the MKS unit, is watt per meter squared. And we just take our luminosity and we divide it by 4 pi times the distance squared. So d here is the distance between the source and the detector. And somewhat related quantity is known as the intensity. So in astronomy, this is called the intensity. In a lot of other literature, for instance in engineering, it's known as the spectral radiance, which might be more helpful when you're Googling. And that's just because intensity is used for lots of things. But astronomers are stubborn, and so instead of spectral radiance, we still use intensity. So this is the energy per unit time and unit solid angle and unit projected angle and unit wavelength. Okay, watt per steradian per meter squared per nanometer. That's emitted by a light source or collected, reflected from a light source. So we'll elaborate more on this in a moment. So the specific radiative intensity is what To Build a Star calls intensity. So here we're using the ray picture of light. So our photons propagate along straight lines, but we have some physical extent to our light. So the light source has some area to it. There's some opening cone emanating from the light source, and the light source might not be perfectly pointed at our detector. It might be oriented at an angle, and so we're going to care about some projected angle, between the light source and the detector, for instance. So just to elaborate that on the picture here, we have some surface area here that is our light source, and this light source, the normal to that is indicated by N1, and so it's not perfectly pointed at the detector. Instead, there's an angle in between the normal of our light source, which is dA1, and the shortest, the vector that connects the detector to the light source. Okay. And then if we pick a given point on our area here, then there's some solid angle, d sigma 1, that describes the kind of light cone that would reach this detector. Okay. So we need to quantize our continuous space somehow. So each ray here is going to correspond to a cone of light with some small solid angle about some direction. Okay, and so if we want to look at the intensity about point P1 here, so it's not just from P1. P1 is a finite point There's no area to it, so this is really some finite area element around P1. Then the intensity here is the little bit of energy slice that we're considering, so some small range in photon energies per projected area, so that's the actual area around point 1 times cosine of the angle between the normal from dA1, the angle between that and the vector connecting these two, the source and the detector. And also in the denominator we have the solid angle, and then we're interested in some wavelength range here and some slice of time, okay, that we're looking at this intensity over. So the differentials here, why do we use differentials? It's because we're just looking at really small slices in energy, angle, and time. So that's our intensity. So when we're thinking about intensity, we want to bring in this concept of Etondu, which I'm probably saying wrong, which is why there's a YouTube link there for you to also sound fancy, and you can say it in the proper French way. So the Etondu is a geometric property of our light cone. It's roughly kind of how spread out the light is. So it's just the projected area multiplied by the solid angle. Okay, so this turns out to be conserved in free space. So if we have no diffusers or absorbers, then our Etondu, this geometric property of our light, will be constant. And the Etondu, so that means it's conserved, in a vacuum. It can also only ever be increased. So if you add a diffuser or an absorber, this will only ever get larger. So how do we prove that the Etondu is constant? Well, let's consider the solid angle from our source to the detector. So if we have some area element on our detector ds, then the solid angle from our an infinitesimal slice of our light source to there, that's the d sigma. So that's going to be equal to, typically we say just the area of the detector element divided by the distance squared, but we need to take into account this projection. So there's also a cosine of theta s there. So that is our d omega. And then let's instead look from the opposite direction. Let's imagine we're at a point on the detector and we're looking back at the source. So that solid angle, d sigma s, that's again just projected area divided by distance squared, but we're considering an area element on the source itself. So okay, so we have these two, this is how you define a solid angle, right? These two definitions. So our Etondu, dg, this is equal to the projected area times the solid angle. So let's do the Etondu for the detector. Well, we can substitute in the solid angle for the detector, that's right here. We do that, and we get that the Etondu is the infinitesimal area element on the detector times that cosine of that projected angle times the infinitesimal area of our source times the projected angle from the normal from the source to the detector, and divided by the distance between them squared. We can do the same thing for the Etondu for the source itself, and we now then instead are plugging in the solid angle, basically definition from our source in there, and you can see that again you have the same things being multiplied by each other, right? You have the product of the infinitesimal area elements, the product of these cosine of these projected angles, and divided by the distance squared, and so this Etondu is constant. And why should you care about that? That means that your intensity is conserved from your source to detector. That's one reason to care about the Etondu. So that's nice when we have our detector, which is extremely far from the star, it's far away. We know that the intensity that we measure, that's the same as the intensity coming from the light source itself. And that is it for these quick notes.